On behalf of National University Management International College and NUM Social Innovation Lab, I'm very pleased to welcome Dr. Alan Lightman to our guest speaker series. Dr. Lightman is an American writer, scientist, and social entrepreneur. He was educated at Princeton and at the California Institute of Technology, where he received a PhD in theoretical physics. Alan has been a professor at Harvard University and the Massachusetts Institute of Technology, and was the first person at MIT to receive a faculty appointment in both science and the humanities. Alan's essays, stories, and articles have appeared in numerous publications such as Harper's, The Atlantic, The New Yorker, and The New York Times. He is the author of more than 15 books and the founder of the Harpswell Foundation in Cambodia. And I should also mention, as I just already previously mentioned, that our current manager of NUM Social Innovation Lab, Ms. Lee Soganya, is also an alumna of the Harpswell Foundation, and we have many of their members also joining us this evening online for this session. So I'm very pleased, therefore, to invite Dr. Lightman to present this evening on the topic of the accidental universe.
Well, let me say, first of all, that I'm very happy to see all of you here. Thank you for joining me and joining us. And I'm honored that Sokanya asked me to give this presentation. I know that a lot of you are studying entrepreneurship, and my topic tonight is really not about entrepreneurship unless there are entrepreneurs in other universes, in which case it might be relevant. Let me get started. Until recently, scientists believed that all the phenomena of the physical universe could be understood as necessary consequences of a small number of laws of nature, sort of like a crossword puzzle that has only one solution. And I'm not sure whether you have crossword puzzles in Cambodia. Would be like, you know, a foot that you're getting a shoe for and it has only one size fits. And when I say law of nature, I mean something like the principle of what we call the conservation of energy, which is that the total energy in a closed system remains constant, even though that energy may change form. Like when you strike a match, the chemical energy of the match goes into heat and light, but if you total up the amount of energy in the heat and light, it equals the amount of energy in the original match. And that's what's called conservation of energy. That's an example of a law of nature. And until recently, scientists thought that everything about the universe could be explained in terms of a small number of laws of nature, like the conservation of energy. And actually, we've been very successful with that assumption. We've been able to explain things like the mass of the electron, which is a subatomic particle. We've been able to explain the orbits of planets, the color of the sky, the size of raindrops, and many, many other physical phenomena we've been able to explain in terms of a small number of laws of nature. And we thought that we actually could explain every phenomena in nature from a small number of laws. But very recently, we have learned that that is probably not true. That starting with the same fundamental laws, like the conservation of energy, that there are a vast range of universes that are possible with many different properties. This would be like going into a shoe store and finding that a size 9 fits you perfectly, but a size 7 fits you just as well, or a size 16 fits you just as well. Some of these other universes might have 17 dimensions, or 13 dimensions, or 20 dimensions. Some might have complex molecules like hemoglobin and DNA, and other universes may have only subatomic particles. Some of these universes might have planets and stars, and some may not. Some of the universes might have conditions that allow for life to develop, and some may not. So starting from the same fundamental laws, it appears that there are lots of different universes possible. And if that's true, it means that our universe is just an accident, a random throw of the dice, one of many possible universes. And if that's so, it means that some aspects of our universe we cannot calculate just in terms of fundamental laws, because an accident plays a role, just like you can't calculate what number is going to come up on a dice when you throw it, on a die when you throw it. This collection of all possible universes is called the multiverse, and some of you may have heard that word before. And I just wanted to say that this finding, which I'm going to talk to you about more, this now understanding that a lot of universes are possible from the same fundamental laws, this is very upsetting to scientists, and it's especially upsetting to theoretical physicists who want to be able to explain everything in the universe as necessary consequences of a small number of fundamental principles. Physicists don't like accidents. They'd like to be able to explain everything in terms of basic principles like the conservation of energy. So in a few minutes, I'm going to explain to you why scientists have come to these disturbing conclusions that our universe is just an accident among many possible universes. But first, I wanted to give you an introduction to cosmology, which is the study of the universe as a whole. And I think that introduction is necessary in order to understand what I'll be talking about later. So I'm going to now, if I can do this, I'm going to share my screen. And let me see if I can do that. Just take me a minute to get the technology right here. Can you see that picture there? That's an early cosmology of an ancient civilization, the Babylonian civilization, about 3,000 or 4,000 years ago. Can you see that? Can you see it, Steve?
Yes, we can see your screen. Yeah. Okay,
good. So this is one of the early ideas of the universe. There's an underworld. The Earth is at the center. There's an underworld where people go when they die. It's surrounded by ocean, of course, and a lot of the early civilizations were on bodies of water like the Tigris-Euphrates River, and they thought that water played a huge role in the universe. Then we have the stars up here, and then we have the ocean of the heavens. So this was about 2500 BC, actually. Then I want to show you a cosmology that came after that. This is a cosmology of the ancient Greeks, so maybe 500 BC on. The Earth is at the center. Then we have some air around the Earth. Can you see my pointer moving?
Yes, sir.
Yeah.
Okay, good. Then we have the orbits of Mercury, Venus, then the orbit of the Sun, and then orbits of the other planets, Mars, Jupiter, Saturn, and then the outside ring is the sphere of the stars. So this was the thinking after the Babylonian cosmology. Of course, it placed the Earth at the center. Now, the ancient Greeks didn't have much idea about how big these things were. I think there was an estimate for the size of the Earth, but there weren't any estimates for how far away the sun was, for example. Then we go to the next cosmology, and this is just a picture of Nicholas Copernicus, who was a Polish astronomer who lived from 1473 to 1543. So we've skipped about 2,000 years into the future. So this is about 500 years ago. And Copernicus was one of the first people to say that it's not the Earth at the center of our solar system, but it's the sun. So then what I wanted to begin talking to you about is a galaxy. And I think that a lot of you have seen this bright, fuzzy, milky looking cloud across the sky on a clear night. And we now know that that's actually a huge collection of stars called the Milky Way. But we didn't know what the Milky Way was. We didn't know whether it was actually clouds in the sky or individual stars or what it was. And we also didn't know how far away it was. In fact, we didn't know how far away any star was, because stars come in a range of luminosities, like light bulbs of different wattages. And you see a light bulb at a certain distance and you don't now know what its wattage is. You have no idea how far away it is. If you were outside at night and you saw a light in the distance, you wouldn't know how far away that light was unless you knew how luminous, how many watts it was. If you knew how many watts it was, then by figuring out how bright it appeared, you could calculate its distance. But if you didn't know its luminosity or its wattage, you wouldn't be able to figure out how far away that little light is. And that's the way it is with stars. When we look up at the sky, we just see this two-dimensional picture, and we have no idea how far away the stars were. If all the stars were the same luminosity, the same wattage, then we could say, well, the ones that appeared brighter were closer, and the ones that appeared dimmer were further away. But we have reason to believe that they're not all the same wattage. So the person who figured out how to measure the distance to the stars was one of my favorite astronomers named Henrietta Leavitt. I don't know, how many of you have heard of Henrietta Leavitt before? Just raise your hand. Probably almost none of you. Well, Henrietta Leavitt, in my view, is one of the most important astronomers of all time. She's not well known by the public. She worked at the Harvard College Observatory in Cambridge, Massachusetts. And she figured out a way to measure the distance of the stars. And what she noticed was that certain stars vary in brightness. And let me see if I can find that. This is the brightness of a star, of a particular star, and time is on the bottom axis and the brightness is on the top axis. And you can see it gets brighter up here, then it gets dimmer, and it's brighter again. These stars pulsate, they oscillate in brightness. And Henrietta Leavitt was able to figure out that their intrinsic wattage was related to the time for them to complete one cycle. The stars that were greater wattage had longer cycle times than the stars with smaller wattage. And so by measuring how long it took one of these stars to complete an oscillation of brightness, she could tell what its wattage was. And once you know its wattage, by comparing that to how bright it appears, you know how far away it is. So it was, in effect, she found a way to measure, to see a little label on each star telling what its wattage was. This was just a certain group, special group of stars. She was able to basically, essentially attach labels to each of those stars by by looking at how long it took it to complete one of these cycles, telling what its wattage was, and thereby computing its distance. And if you could find these special stars at different places in the Milky Way, you could measure the size of the Milky Way. And what she found was that the Milky Way is about 100,000 light years across. And now let me say what a light year is. A light year is the distance that light travels in a single year. Now that a light beam can go around the Earth 7 times in 1 second. That's how fast a light ray is. And the distance that a light ray can travel an entire year is called a light year. So Henrietta Leavitt was able to show that the nearest stars are maybe 5 or 10 light years away, and the Milky Way as a whole is 100,000 light years in diameter. It would take a light beam 100,000 years to go from one side of the Milky Way to another. The distances in space are so vast that we measure them using the light year as a measure of distance. So let me go back to screen share. And I'm going to show you this is a galaxy like the Milky Way. Of course, we can't get outside of the Milky Way to see it from a distance. This is called the Andromeda Galaxy. It's about 2 million light years away, or about 20 times the diameter of the Milky Way. And it's very similar in shape and appearance, we think, to the Milky Way. So with Henrietta Leavitt's method of measuring distances using these special kinds of stars that oscillate in brightness, we were able to determine that the Andromeda Galaxy is outside of our galaxy. First of all, it's outside of our galaxy because our galaxy is only 100,000 light years across, and this is 2 million light years away. And we were also able to learn that the other little points of light and spirals in the sky, those are all galaxies. And here's a picture of the star taken with the sky taken with the Hubble telescope, looking very, very far out. Now, millions and millions, hundreds of millions of light years out. And we see all of these galaxies out there. Each one of them is a collection of about 100 billion stars. And an important point to emphasize is that when we look further out into space, we're looking backwards in time. Because if we see the Andromeda, for example, when light from the Andromeda reaches us, our telescopes, Andromeda is 2 million light years away. That means it took 2 million years for light to go from Andromeda to us. So when that light first hits our telescope, we're seeing what Andromeda looked like 2 million years ago. And we look at a galaxy that's 100 million light years away, we're looking back 100 million years into the past because it took light 100 million years to get from there to here. So outer space is a kind of time travel. The further out we look, the further back in time we're looking. And this is all because light has a finite speed. If light had an infinite speed, if it could go from there to here in no time at all, whenever we looked out, we would see all these galaxies just as they are right now. But light doesn't have an infinite speed. Well, now I wanted to go to the next important element of cosmology, which is that our universe is expanding. And this was discovered by this man here, another American astronomer named Edwin Hubble. in 1929, Edwin Hubble, with his telescopes, found evidence that the universe is expanding, that all of the galaxies appeared to be moving away from us with a speed proportional to their distance. And let me give you an analogy there. Suppose you have a balloon and you put dots on the balloon, and each dot represents a galaxy, and you start blowing up the balloon. Well, the dots are going to start moving away from each other. And from any one dot, it appears that all the other dots are moving away from it, but there really is no center on the surface of the balloon, because it looks the same from the point of view of any single dot. So Hubble found that the other galaxies were moving away from us at a speed proportional to their distance, which is exactly what you would get if the whole universe were a balloon that was being blown up. So the universe is expanding. The universe is expanding. And if you play this movie backwards in time, if you imagine going backwards in time, the universe is then contracting, you can calculate when all of the galaxies in the universe were on top of each other. If they're moving away from each other now, that means if you go backwards in time, they're getting closer and closer and closer together. And you can calculate a moment in the past when all the matter in the universe was crushed to a single point. And that time is about 13.8 billion years ago. We know it pretty precisely. That moment in time when all the matter of the universe was compacted to a region smaller than a single atom, that's called the Big Bang. That is considered to be the beginning of our universe, and we can calculate that it's about 13.8 billion years ago. So if we found anything in the universe that was older than 13.8 billion years, it would contradict that theory. But so far, everything that we have found in the universe, including the age of the Earth, the age of the sun, the age of the oldest stars, is less than 13.8 billion years ago. So we have pretty strong evidence that the universe began about 13.8 billion years ago. But not only do we have this sort of evidence of that, but we have detailed theories. Let's see. We have detailed theories to show how the universe evolved. We think at the beginning of let me share my screen again. Near the beginning, near t equals 0, near the beginning of our universe, we think that first there was just energy, and that energy changed into particles, and we had random particles whizzing around very near the beginning. Well, we actually have a theory that can calculate very accurately what the conditions will look like at the beginning of the universe. And let me see if I can show you that. This is a calculation. You don't have to pay much attention to the details, but the point I wanted to emphasize is that here's the temperature of the universe starting at t equals 0, the beginning, going up to, there's 1 second. That's 1 second right there. When the universe is 1 second, you can see how much happened between t equals 0 and 1 second. Here's where we are right now, 10 billion years, 13.8 billion years later. Here's the density of the universe as a function of time. It decreases with time. The temperature decreases with time. The point is, we have a detailed mathematical theory that shows how our universe behaved since t equals 0. Now, when the universe is about 1 second old, right around here, these particles that were whizzing around, some of them began sticking together due to the nuclear force. The nuclear force is a force that pulls the subatomic particles and the nucleus of the atom together. And the protons and neutrons, which are type of subatomic particles, stuck together, pulled together by the nuclear force to make heavier nuclei. Here's deuterium, then we form tritium, then we form helium. Hydrogen and helium are the two lightest elements of all. Carbon, oxygen, silicone, all the things that our bodies are made out of are much heavier atoms, much bigger atoms than hydrogen and helium. And we believe, and I'm going to explain why this is important in a minute, that in the early universe, when the universe was a couple of minutes old or less, that hydrogen fused to make helium, not all of the hydrogen, but some of the hydrogen, but the universe was thinning out and cooling too rapidly to make heavier elements. It was expanding too rapidly and cooling too rapidly to make carbon and oxygen and other elements. So only hydrogen and helium were made in the early universe. And we think that all the other elements, carbon, oxygen, iron, silicon, magnesium, all the other elements that our bodies are made of came much, much later. They were made at the centers of stars. And we know that in stars, that the conditions at the centers of stars are very dense. They're not expanding like the early universe was. And all of these subatomic particles stay together. They're held together by the gravity of the star. They're whizzing around, and helium atoms can fuse together to make carbon atoms. Carbon atoms can fuse together to make silicon atoms. And all the atoms in our bodies, except hydrogen and helium, were made in the centers of stars. And certain stars bigger than about 10 times the mass of our sun explode into what's called a supernova. So the stars explode and they spew all of these heavy atoms like carbon and helium, carbon and silicon and oxygen. They spew them out into space. And then when solar systems form, like our solar system and planets, they form out of this material that has been ejected from stars. So that's where life comes from the elements that are created in exploding stars. And if you can't create a star, you can't create carbon and oxygen, all the elements that are made for life. So that's my long background of cosmology. And now I'm going to return to my original question, which is, why is it that scientists think that our universe is only one of many universes and our universe is just an accident? Well, there are two reasons why scientists have come to this conclusion just in the last 50 years. One is that there's certain odd features of our universe, and I'll say what that is, certain properties that are hard to explain unless there are many other universes. And secondly, we have certain theories in physics that actually predict the existence of other universes. First of all, the odd features. Back in the 1960s, some scientists began to notice that there were certain numbers, parameters in our universe that if they were a little bit different, a little bit bigger or a little bit smaller, that life would never have developed in our universe. And one such parameter, example, is the strength of the nuclear force. The nuclear force is the force that holds subatomic particles together at the centers of atoms. And if the nuclear force were just a few percent larger than what it actually is, then all of the hydrogen in the early universe would have fused to make helium. There would be no hydrogen left. And without hydrogen, you can't have water. Water, you remember, is H2O. It's two atoms of hydrogen and one atom of oxygen. So there would be no hydrogen left in the universe. And most biologists think that you need water to have life, even if it's life very different from ours. Another example of an odd feat. So the question is, why is on the other hand, if the nuclear force were a little bit weaker than it is, a few percent weaker, then the heavier atoms like carbon and oxygen would not be able to hold together, because you need a strong nuclear force to hold large atoms together. The electrical repulsion between the particles is trying to push the particles apart. So you need a very strong nuclear force to hold the subatomic particles of carbon and oxygen and the heavy elements together. So if the nuclear force were a little bit weaker, we wouldn't have complex atoms. We would only have hydrogen and helium. And we think that you need complex atoms with lots of chemical connections to make life. So the nuclear force appears to lie in a narrow range that allows the development of complex atoms. Secondly, in 1998, we discovered that the universe is not only expanding, but it's accelerating. The expansion is increasing in time. And we know it's accelerating because nearby galaxies are moving away at a faster speed than faraway galaxies. And we know that the nearby galaxies are closer in time to us. They're more recent, where when we look at distant galaxies, that's looking back in time. And the universe was expanding more slowly further back in the past than it is now. So the universe is accelerating, and we believe that it's accelerating due to an energy field called dark energy, which you may have heard about. We've measured the amount of dark energy, and it's equivalent to one lighted match in space every 10,000 cubic kilometers of space. The energy of one match lit in every 10,000 cubic kilometers. Now that may seem like a tiny, tiny amount of energy, but over millions of light years, that builds up, and in fact is the dominant force in the universe right now. Now, what scientists have concluded is, just like the nuclear force, if the dark energy were a little bit bigger than what it actually is, the universe would be expanding so rapidly that galaxies would never form. And if you don't form galaxies, you can't form stars. For a galaxy to form, you need gravity to overwhelm the outward expansion and pull everything together. But if the universe is accelerating too rapidly, gravity can't compete with that acceleration, and you can't form galaxies. Things are pulled apart too rapidly to form galaxies. On the other hand, if the dark energy was a little bit less than what it actually is, the universe would collapse before you have time to form stars. Instead of accelerating, the dark energy would cause a deceleration, and the universe would collapse before it has time to form stars. Now, if you remember from my earlier discussion, stars are absolutely critical for life to form, because you need stars to form the heavier atoms like carbon and oxygen. If you didn't have stars, all you would have is hydrogen and helium in the universe. And those two elements are so simple. It's just either one proton or two protons and one neutron, two neutrons. You wouldn't have enough complexity to form all of the chemical elements, the chemical structures like hemoglobin and tissues and all the things that life is made out of. So it appears, and there are a lot of other parameters that appear to be in a narrow range to allow life. That is, if these parameters were a little bigger than they are or a little smaller than they are, then life would never form. So this is a great puzzle. Why should the universe care about forming life? Why should life matter to our universe? Why does our universe have just the right properties to create stars and heavy chemical elements and solar systems and planets and life? Why does it have those properties? Well, one explanation is the explanation of intelligent design. I don't know if any of you have heard of intelligent design before. Would you put a thumb up or something like that? Yes. Anybody else heard of intelligent design before? Anybody else? Intelligent design is an argument for the existence of God. And the argument goes that the universe appears to be designed so perfectly that only an intelligent being could have designed the universe this way. And that's one of the arguments given for the fine tuning of these parameters of our universe, that God wanted there to be life in our universe. And so God made the universe with the right strength of the nuclear force, with the outright amount of dark energy, and so on, to allow the existence of life. That's one argument to explain why all these parameters appear to be in a narrow range. And there are a number of people who believe that argument. But most scientists don't like that argument. Most scientists are atheists or agnostics, and they want to be able to explain the universe without invoking the existence of God. So their explanation, the scientific explanation, is maybe there are lots of other universes beside our universe with different properties. Some of them have large values of the nuclear force. Some of them have small values of the nuclear force. Some of them have a lot more dark energy than our universe does. Some of them have a lot smaller dark energy. Most of those universes would not allow the existence of life, but some of them do. And we happen to be in one of those universes that has the right parameters to allow the existence of life. And let me give you an analogy to this kind of explanation, that there may be lots of other universes. Suppose we notice that the planet Earth, our planet, has very favorable conditions for life. We're just the right distance from our sun to have liquid water. If we were closer to the sun, like Venus, it would be so hot that all the water on our planet would have boiled away. And if we were far away, like Pluto, it would be so cold that we wouldn't have liquid water. Any water would be frozen. And we believe that liquid water is necessary for life. Liquid water has a lot of wonderful properties that allow chemical reactions to go on. It allows chemicals to go back and forth through cells. Biologists believe that you probably need liquid water. But there are other properties of our planet that are also very favorable for life. We have oxygen on our planet, which is certainly necessary for the kind of life that we have. So if there were no other planets in the solar system, you might ask the question, isn't it amazing that our planet, our one planet, has just the right conditions for life? It has oxygen, it has liquid water, it's just the right distance from the sun. Isn't that amazing? And you might say, well, God must have made our planet because God wanted life, and look, we have all the right conditions. But we also know that there's another explanation, which is there are lots of planets in our solar system, and lots of other stars have planets around them. And we know that the other planets in our solar system probably don't have life. They don't have the right conditions for life. Venus is too close. It has an atmosphere of sulfuric acid. It's too hot. As I was saying before, Neptune and Pluto are too far away. And so that kind of explanation is like the multiverse explanation. There are lots of other planets. Most of them do not have the right conditions for life. But our particular planet is the right distance from the central star to have the right conditions for life. And in fact, we know now that there are lots and lots of other planets in the galaxy that are also the right distance from their central stars to have liquid life. But many other planets don't have the right conditions. So that's the same kind of explanation as the multiverse. The multiverse explanation is, look, we're not the only universe there is. There must be lots of other universes that have different properties, and we happen to be in a universe that has the right properties for life. Otherwise, we wouldn't be here to talk about it. So let me give you an analogy, and it's what I call the intelligent fish analogy. Suppose you have some very smart fish, and of course, fish live in the water, and their bodies are designed for the water. And one day, some very intelligent fish, some philosopher fish and physicist fish say, isn't it amazing that our world is all made of water? Because if there wasn't water here, we wouldn't survive. I mean, isn't that amazing? And the fish develop various hypotheses for why their world has to be water. They concoct a lot of theories to explain why you can't have any kind of existence at all without water, but they can't ever quite complete their calculations, that they can't ever totally prove that things have to be water. And then one day, some very old fish who are smart but have wisdom have this hypothesis. Maybe there are other places that don't have water, that are dry land. And maybe we happen to live in a place that has water because otherwise we wouldn't exist. But there are other places in the world that are dry land. So that's sort of like the multiverse hypothesis. Now, I want to leave some time for questions. So let me just say very quickly that there are a couple of theories in physics that actually predict the multiverse, actually predict that there are other universes. One of those theories is called string theory, which you might have heard of. And string theory predicts that there are lots of other universes possible besides our universe. Another theory is called chaotic inflation. And let me just see if I can show you an example of chaotic inflation. I know I have. Just a minute here. Chaotic inflation is a theory that has been very successful explaining certain properties of our early universe. And chaotic inflation predicts that each universe can spawn a new universe in a picture that looks like this. I wanted to say that we haven't proved either the chaotic inflation theory or string theory. And in fact, we can't prove that other universes exist. because by definition, a universe is a region of space and time that is totally disconnected from other regions of space and time, even if you go infinitely far into the future. That's what defines a universe, a region of space and time that is cut off from all other regions of space and time, even if you go infinitely far into the future. There's no way that you can communicate with other regions of space and time. And each of those regions that can communicate with itself is called a universe. But we can't prove that other universes exist because by definition, we can never communicate with them. So physicists have found themselves in this sort of very uncomfortable position where we think that we need the multiverse hypothesis in order to explain certain odd features of our universe. But we can't prove that these other universes exist. So we have to take their existence as a matter of faith, a belief in our theories, which has a certain irony to it, because people who argue that we have intelligent design, that we have a God that created our universe, are also making that statement on the basis of faith, because you can't prove or disprove the existence of God. So it's a very interesting situation that modern physics has gotten itself into, where we think we need to invoke the existence of something that we cannot prove. I'll end my formal talks there. I want to allow 10 or 15 minutes or so for questions. Yeah. Can you unmute your mic?
Hello, Professor. Actually, I have a question related to the string theory. Like, for example, if we have this kind of like orange, and then we just want to figure out like the smaller component in here, and then it actually make out the subatomic, like the atom. And inside the atom itself, it might have this kind of like neutron, electron, and especially in the proton itself, it have this kind of like quark. And
right.
Yeah. And that's something related to, I mean, like from the each quark to another, that related to the string itself. So I think like in this planet itself, we have like 3 dimensions, right? We have the forward, backward, left and right, and up and down. But I think we might have another more than that, because the way that string they work, it's just not in that dimension.
Correct. That's correct. String theory predicts that we have 10 or 11 additional dimensions besides the 3 that you mentioned, up, down, and sideways. And we don't see those, according to string theory, we don't see those extra dimensions because they're curled up in ultra tiny loops, very, very tiny loops. Just like if you looked at a hose, a water hose from a great distance, it just looks like one-dimensional because you can't see the other 2 dimensions. So you're right, string theory does to predict other dimensions. However, even starting with string theory, there are many, many different possible universes. There are universes with a strong nuclear force, universes with a weak nuclear force, universes with a lot of dark energy, universes with a small amount of dark energy. So string theory, everything you said about string theory is true, but it does predict that there are many different possible universes starting from the same fundamental laws of nature.
Yes, sir. Sure. And one more thing related to the vibrating of the string itself. Like actually in the universe, we have a different type of property, like with different size. Some are small and some are huge. So that really depends on the difference of that string, or because of its frequency of that string, that make property becoming different from one another.
Yes, it's believed that these very, very, very tiny strings of energy, and they're not matter, they're really energy, are vibrating like strings on a violin, and the different strings are vibrating at different amounts, and those vibrations produce the subatomic particles that we see. But the basic point, the important point for this lecture is that string theory predicts many different possible universes with different parameters. That's the important point for this lecture. And it sounds like, Ruxmai, that you have studied string theory, so I congratulate you for that. Are you a physics major?
Actually, I'm studying architecture.
Your education?
Actually, like I like astrophysics. I like to study there, but I think we don't have the opportunity in Cambodia. But then I pursued another major in architecture. But I still like, you know, like being. I like about the astrophysics, about the universe and cosmos, and I don't have really a lot of knowledge regarding to that. But I like reading the book related to the interstellar or the book of the nether crescent.
Yes. Well, I hope that you can get a scholarship to a university outside of Cambodia. If you send me your email address, and Kanya has my email address, I can send you a couple of my books about astrophysics that I've written myself. But I hope that you will get a scholarship to leave to go outside of Cambodia and study astrophysics.
Thank you, sir.
Any other questions?
I think I just want other to ask for. Yeah.
Yes. Someone else have a question? You have to unmute your mic to ask a question.
Yeah. Hello, Professor Allen. Yeah, can you hear me?
Yes.
Okay, good. Yeah. Yeah, I just posted a question inside the chat. I read somewhere that gravity might be a way of even communicating or sending information from one universe to another. That it could be this mysterious. Currently, we don't know what gravity actually is, so you know the hypothesis that it might be a thread that binds all of the universes together. What do you think about that? Is that possible? Or?
Well, it's possible, but we have very, very little evidence of that. That's the brain called the so-called brain theory of cosmology. There's no evidence for that. It doesn't mean it's not possible, but we just have no evidence for that. And we would need to have a theory of quantum gravity, that is a theory that merges quantum physics with gravity, in order to understand that, whether that's possible or not. So that's I would consider that to be a speculation at the moment. But you're right. That is a proposal, but I would consider that to be very speculative.
It's
a lot of uncertainty.
It's a nice thought in a way.
Yeah,
it's a pleasant thought in a way. Otherwise, you know, just this very isolating thought that there's this infinite number of universes in all directions going on forever that we'll never be able to communicate with.
It is isolating.
It's a bit dark and depressing.
But there's no reason why Mother Nature has to obey our ideas of comfort and convenience and aesthetics. Nature may not be what we would like nature to be. I mean, it's also very isolating to think that there probably are many other civilizations in our universe, you know, just the one universe we know, that there are probably many civilizations, probably some of them that are more advanced than us, that we will never be able to communicate with because the distances are so huge. So that also is a little bit disturbing.
Yes.
So nature made the universe such that stars are very, very far apart. We may never be able to communicate with other intelligent life, even though almost all scientists are 99.9% convinced that other life exists elsewhere in the universe. And of course, probably some of it is a lot smarter than us.
Yeah.
Another question?
Hi, Professor.
Yes. Let me click view.
I'm using my fiance's laptop,
Yeah.
so I'm not
So-
exactly Cambodia, but she's
Yeah,
with me.
we're here together. He has a
So,
question.
are you as beautiful as your fiance?
Not as beautiful. That's why I keep the video turned off.
Okay. Right. Smart man. Yep.
Well, thank you so much for such an interesting presentation. I really like the intelligent fish example. That just reminds me of a quote about how if triangles has a god, they would give him 3 sides. But
Yeah.
my question is, I think I'm particularly struck by your last remark about how, ironically, scientists go a full loop, right? I mean, they believe that there are multiple possible universes, even though, I mean, I think what you mean is they cannot prove it empirically, but of course, theoretically, it can be proved. So,
right, it can be proved theoretically, but science is an empirical subject. I mean, even though theory is very, very important to science, that in the end, if you have a theory that you can't prove or you can't disprove, it's more philosophy or theology than science. Even Einstein kept coming back to experiment. That his theory of relativity was based in part on experimental data, like the fact that all objects fall with the same acceleration and gravity, independent of how big they are. He was tuned into the world of experiment. So science, I mean, I think that what distinguishes science from the humanities, from all of the humanities, is that it is in touch with physical reality, that experiment is central to the enterprise of science. So if we can't test a theory, if we can't do an experiment to test a theory, eventually that theory becomes more of a branch of philosophy than science. And that's one of the difficulties that modern physics has gotten itself into with string theory, which we can't test either. We haven't, because strings, even the biggest particle accelerators that we have in Switzerland cannot accelerate particles up to a high enough speed to test string theory.
I think that actually is part of my question, right? When science advances to that level where it's actually by definition impossible to prove something empirically, or at least it's not possible at this point. By what criteria do scientists actually evaluate different theories, right? For example, people may say, okay, one group proposes string theory, the other group proposes the chaotic expansion theory that you spoke about.
Right.
Some people are saying we are just a simulation in AI world. Some
Right.
people, assign everything to intelligent design. So
right.
by what criteria should we actually evaluate a lot of these different?
Well, that's a great question. That's a great question. Here's what my answer is to it. The way that we evaluate theories that we can't test is we look at pieces of the theory that we can test. And if pieces of the theory can be tested and agree with experiment, that gives us greater confidence in the whole theory, including the parts that we can't test. It's like if you see a tail of a tiger coming out from underneath the door is closed and just the tail is sticking out. You don't know for sure there's a tiger behind the door, but you have seen a tiger's tail before. And you can measure the tail and compare it to other tiger tails that you've seen. That would be a reason to believe that there's a tiger behind the door. In the case of chaotic inflation theory, which is one of the theories that I said predicted the multiverse, it does make predictions about this cosmic bath of radio waves that we see coming from all directions. It's called the cosmic background radiation. It was first measured in the 1960s. It's radio waves that come from all over the universe, and we think that these radio waves were created in the Big Bang, and we can measure their properties very, very accurately. Not only their spectra, the way that they fluctuate from one part of space to another, and the chaotic inflation theory makes a very accurate prediction about what these radio waves should look like, and it agrees with what we actually observe. So that's a piece of the chaotic inflation theory that we can test in our universe. We don't have to go outside of our universe to test that piece of the chaotic inflation theory. So that's like seeing the tiger's tail under the door and recognizing that it looks like all other tiger tails you've seen. And if we can test that piece of inflation theory, then it gives us some belief that maybe the rest of the theory is right, even though we can't test it. So those are the kinds of things we do, the criteria that we use to compare different theories where some of the predictions of the theory are untestable. Does that answer the question?
That is very clear. Thank you so much. And I really do look forward to reading your book. So I'm just going to get it on Kindle right now. Thank you so much.
You're welcome. Any other questions? Roxmaya is another one.
Yes, sir. I'm still curious about the question like, how does the string theory state the universe operated with 10 dimensions? I mean, like, I know this kind of like from the documentary, but I don't really know how. And it also stated that like the string theory is initially happened before the Big Bang. Is that right?
Well, yeah, well, we think that there must have been something before the Big Bang. Some kind of quantum foam. We think that, of course, quantum mechanics, which is a branch of physics that I don't have time to explain, but I'm sure many of you know about it, that there was some kind of quantum reality or quantum existence that created our universe. Stephen Hawking believes that our universe was created out of absolutely nothing. But of course, there had to be laws of physics from which the nothing came. And where did those laws of physics come from? So you asked, how does string theory make the universe? Well, only 3 of the dimensions of string theory are large dimensions, which would participate in everything that I described, the energy and particles in the early universe, protons and neutrons sticking together to make helium, the formation of stars. All of that would come from the 3 dimensions of string theory that we know about. The other 7 dimensions are curled up into ultra tiny loops, and we would never experience them. Not only we, but even a proton or a neutron or a quark would never experience them because they're even much, much smaller than quarks. So it's like, well, let me see. I guess it's like the garden hose. If you could use the garden hose, but always at a distance so far away that the width of the garden hose never mattered, and all that mattered to you was the water that came out of the garden hose. Any other questions? There must be a few other.
Like one more thing related to the planetary, for example, like the Earth. Before, like if we go back to 2 billion years ago, like the Earth, it have completely a different atmosphere compared to the current day, which means like it's full of flame, it's full of like volcano eruption. But then like in the future, it still can support life because it have these kind of like hydrogen and that can create water. I think like that can potentially be happen to the other planet in our solar systems, because like currently we don't see there are a lot of like a good atmosphere like the Earth.
It could have happened. I mean, if you take, it's possible, but most biologists think there would be some signs of life. There would be some chemicals on those planets that would be indicators of life. And you might have read that very recently, scientists found in the atmosphere of Venus, a chemical called phosphine, which we believe might be an indication of life, because we think that phosphine can be created only by living organisms, but we don't know for sure. There may be non-living chemical processes that produce phosphine. So it is possible that some of the planets in our solar system had life in the past. It's very unlikely that Neptune and Pluto would have had life in the past, because they're very, very cold, and they would have been cold even in the distant past, too cold for liquid water. But we don't know for sure. And of course, a big area of astronomy deals with the search for life outside of the Earth and outside of our solar system.
Yes, sir.
Anybody else? Rex Mai has asked me a lot of questions. Anybody else?
How are we for time, Alan? Are you okay for time? Or
I'm fine to go another 15 minutes or so, as long as there's an interest in going a little longer. But I'd love to hear questions from somebody else who hasn't asked a question.
Oh, just a quick question. I heard like you talk about multiverse. So beside our universe, there are the universe that you believe or any other scientists believe in. And I wonder, in the universe that it contains only hydrogen and helium, what kind of creature can live in such conditions?
Well, that's a great question. Well, it's hard to imagine any kind of creature that could live only with hydrogen and helium, because you need a lot of chemistry to make the structures that make, for example, neurons, or even any kinds of structures that can store a lot of information. Let's reduce life to just information storage, okay? I mean, we think that someday we might be able to transfer a large part of the memory of our brain onto a computer. So let's just talk about information storage. You need pretty complex atoms beyond hydrogen and helium to store information. Helium only has the helium atom only has 2 electrons. And you can't do much with only 2 electrons. Helium can't really bind with other atoms with just 2 electrons. I mean, if you just have helium, pure helium, you can't really store information. So if you think about life in a very abstract term as information, you can't have information storage with only hydrogen and helium. So from an information theoretic point of view, a universe with only hydrogen and helium could not have any kind of intelligence, anything that we would associate with intelligence, or even elementary life. I mean, even the most elementary life that we have on Earth, like amoebas or viruses, have a huge amount of information storage. Take a virus. A virus has RNA in it, ribonucleic acid, which has carbon and silicone and oxygen, magnesium, all kinds of heavy elements, heavier than helium and hydrogen, to allow all of that information to be stored in a virus. So that's why we think that if only hydrogen and helium existed in the universe, and there must be universes that have only hydrogen and helium, if the multiverse hypothesis is true, they would not have life. Life seems to require pretty special conditions.
Thank you. Thank you so much.
Thank you, Pise. Other questions?
I do have a question.
Yes, sir.
Okay.
Who is this?
It's so
This is
long.
so long. Okay, so long. Nice so long.
Hi, Dad. So, as we know, Albert Einstein developed the theory of relativity. So, and the general or basic idea of the theory explains how objects attract to other objects and how gravity is warping the objects in space. So, are there any scientific evidence that prove how space and time are warped in the universe?
Yes. Well, Einstein has developed what we still consider to be the modern theory of space and time, first with his special theory of relativity in 1905, and then his general theory of relativity in 1915. And according to the general theory of relativity, gravity, which is caused by all masses and energy, creates the geometry of space and can change the flow of time. That is, it can make time go faster if you're far away from a gravitational object. If you get very close to a gravitational object like the sun, or even more extreme gravity like a black hole, time slows down. And this was all described in 1915 by Einstein's theory of general relativity. And all of the tests that we've done of general relativity confirm it. You can't ever prove that a scientific theory is true because you don't know whether tomorrow there might be some experiment that disproves it. But you can confirm predictions made by the theory, and that gives you confidence in the theory. And all of the predictions made by Einstein's general theory of relativity about how gravity changes space and time have been proven. So that's the theory that we have of space and time due to Einstein.
Hello, Dad.
I'm sorry, Rob.
Hi. So I listen a lot about the universe and things, but and you mentioned about the universe is expanding.
Yes.
From each other. So I was wondering why the universe is expanding, and
yes.
Is there any point that one universe is expanding close to, might be in the very far future, the universe can be like collide,
can touch another universe, can collide with another universe.
Yeah,
that's a great question. Well, the universe is expanding because it was created when the universe began at t=0. There were some universes that were expanding and some that were contracting, and only the universes that were expanding could last long enough to create stars and create life. So we have to be in one of those expanding universes, because otherwise we wouldn't be here to talk about it. So it's the same as the multiverse explanation. Your question about whether one universe could bump into another universe, that's a great question, and we don't really know the answer to that question. We don't know how far apart the different universes are. We think that most likely, but we can't prove it, that the different universes are creating time and space around them in such a way that they cannot touch each other. But we can't prove that, and just the same way we can't prove the existence of other universes. But it's a great suggestion that you make, that maybe one universe could expand into another universe, and then we would have evidence of the other universe, because we would have contact with it. But we can't prove whether that can happen or not.
Okay, thank you, Dad.
When it comes to the multiverse, this picture of lots of different universes, there's very little that we can prove. It's the same way as the intelligent fish. They can't prove that there must be dry land somewhere else, but they think that that's a reasonable hypothesis.
Okay, then. Thank you.
Thank you, Soy Right.
That I do also have a question.
Hi, Horn.
I was quite interesting when you mentioned about the Big Bang theory. Because mostly I'm not sure like how science would actually test out something more like an invisible or intangible objects, because so far we have found that life or objects on Earth are actually came after the Big Bang. So what came before the Big Bang, and was there nothing at all?
We don't know what came before the Big Bang. We have theories, but we don't know. But we are pretty sure that our universe began a certain finite time in the past, because we can measure very accurately how fast our universe is expanding, very accurately to within 1% or so. And if we just play that movie backwards, we can calculate a definite time in the past to within 1% of when all the matter in our universe was crammed together on itself. The calculations that I showed you, where I showed you the graph of the temperature decreasing in time and the density decreasing in time, we can use those calculations to calculate how much helium was produced in the early universe in the first 3 minutes. And the amount is about, there's about 12% of the universe is helium, and that agrees very closely with the observations. That is, even though we have a lot of carbon and oxygen and other elements in our universe, most of our universe is still hydrogen and helium. And we can calculate how much helium relative to hydrogen there should be from our Big Bang theory, and we can also measure it with our telescopes, and the two are in pretty close agreement. And that gives us even greater confidence in our theory of the Big Bang. So we have several different ways of confirming our theory of the Big Bang. But we don't know what came before the Big Bang. We need a quantum theory of gravity to do that. And so far, physicists have not succeeded in merging quantum physics with gravitational physics. We have not found a quantum theory of gravity yet, but we think that we will at some point, and then we'll have a better idea of what came before the Big Bang. But it's a great question.
Thank you, Dad.
Could you have multiple Big Bangs? Could you have an expansion, contraction, and then another Big Bang? So could we have had another Big Bang before the Big Bang that we can trace the origin point?
Yeah, we think not in this universe, but you could have lots of other universes having Big Bangs. The reason why we think not in this universe is because of what's called entropy, disorder. That one of the laws of physics is that every system gets more and more disorderly in time. That's called the second law of thermodynamics. And if our universe had gone through many, many expansions and contractions, it would be much more disorderly than it is now, because it would have lasted much more than 13.8 billion years. But what we see a lot of order in our universe, which means it could not have gone through a lot of Big Bangs. Our particular universe could not have gone through many cycles. But the idea that you just proposed was proposed by other physicists in the 1930s, that maybe we had an oscillating universe that expanded, contracted, expanded, and contracted. And it took some years before people realized, no, that would violate the observation that our universe has a lot of order in it. but it's a very good suggestion.
Any other-
I'll go about 5 minutes more, if that's all right with everyone. And of course, anybody's willing to sign off when you want to.
This has been an amazing session, and I'm also very impressed by the questions. They are beyond my expectations. So I'm curious.
Right question. Well, I hope that some of these questions will allow your students to be business entrepreneurs and innovators. But that kind of good questioning and critical thinking, I would think would be good in every field.
And I think the curiosity, you have to be curious and be interested in other disciplines, and the creativity and the innovation comes from, urging or connections between different disciplines.
Yeah, and I think the world has become more and more interdisciplinary as we've gone on. I mean, if you just take climate science, which involves so many different disciplines, but the world has gotten more interdisciplinary, and you need to know more about different areas other than your own, which also means that you need people who can communicate, who can across disciplines, who can talk to people from other specialties and be able to converse with them.
Yes. And my concern always in Cambodia with education is it's a bit too one-dimensional, right? With people just studying law or business or a specific. In the liberal.
Well, it's certainly good to have a core specialization, to be deep in at least one field, but then to branch out from there. If you're only an interdisciplinary and you have no deep learning in any one field, then that also is a problem.
So it's like a T where you're going for the depth on the T and the breadth on the top of the
exactly. Right.
Any more questions?
Well, I've seen a lot of Hartswell students that I haven't had time to say hello to. So see Siuchiata, Chanra, Sawada, many students who I love. Seha, who is in the U.S. Nok Chen, want to say hello to all of you, and I've missed some of the other ones. I'm sort of frustrated that I can't have a conversation with each one of you individually, but thank you so much. And I'm really proud of all of our Hartswell students who have done great things in the world. And of course, also, I'm proud of all of the other students and young people who are part of this program at NUM. And just the fact that you wanted to tune in to this conversation shows a certain amount of ambition and curiosity and interest in the world. I know this is not a topic and a subject that would normally cross your way. So the fact that you've shown an interest in it is very encouraging to me. I think our world today is in such trouble without getting into politics. There are problems everywhere around the world. And it's only our young people that can save us. So I put my hope in all of you young people to do good things in the world and to try to help your societies, because that's what we need. We need to have people who are not thinking only about themselves, but thinking about their society.
Okay, so thank you, Alan. I think there's a lot going on in the chat here. When I'm looking at the chat here, I think of a lot from the Hartswell group here. But this has been an amazing session. I really appreciate your time, and we should do more of this in the future. And it obviously, as you mentioned, it shows that people are interested in astrophysics, which is great to see. When we put this topic together, we were promoting it a lot with obviously our business students, and we weren't sure exactly how they would view the topic. But this has been amazing, great questions, and beyond my expectation. And I think we should be doing more of this. And we do have an upcoming talk with Tony Wagner, actually, from Harvard, who will be talking about education, an education specialist on innovation. So he has agreed to give a session, a similar session for us next month. So this will be a continued guest speaker series that we're opening up to the public, especially during this time of COVID. And we've been very honored to have a lot of people agreeing to do these types of sessions. So, and again, thank you for your time, and have a great day in, I guess, your morning in Massachusetts.
Well, I wish everyone a good evening, and I'm so happy to see many of you. I'm happy to see all of you. Some of you I know, and I'm impressed by this series of lectures that you had, with which So Kanya introduced me to, and I'm honored to be part of it. So thank you, Steve and Kanya.
Thank you.
Bye-bye.
Thank you. Bye.
Thank you.